Hi physics, it's Mr. Fumato here coming to you from the Menlo Physics Lab. I have an interesting demonstration for you. I've got a steel ball here about 5 pounds. It's a pretty heavy steel ball and it's hanging from a string. And there's also a string connected to the bottom of it, and I'm going to ask you a couple of questions. So if I pull down on the bottom string, the question is, which string will break first? The top or the bottom? Again, I'm going to pull down on the bottom string, and the question is, which string breaks first, the top or the bottom? Think about that for about 10 seconds. So let me do the experiment. It turns out that the answer to this depends on exactly how the pull is applied to the mass. If I pull quickly, like for example with a quick little jerk, watch what happens here. The bottom string broke first. I can get the opposite result by pulling down on that bottom string slowly. Watch carefully. The top string broke first. So now that you've seen this demonstration, I'd like to take you through some of the thinking involved, because while the demonstration itself is kind of a fun little puzzle, it turns out that there's some pretty deep and kind of important physics embedded in this demonstration. So let me remind you that the question was, which string breaks first when you pull down on the bottom string? The answer that we saw was that it depends. If it's a quick pull, there's too much mass in the ball. The inertia of that mass will resist transferring that applied force up to the top string, and if you pull quickly enough, you'll just break that bottom string. On the other hand, if the pull is slow, then the mass does have time to transfer the force up to the top string, and then the top string breaks first because it's supporting both the weight of the ball and your external applied force, while the bottom string is only working with the applied force and not the weight of the ball. So again, the inertia of the inertia of the ball is important when you pull quickly, and then it's the weight of the ball that becomes the dominant effect when you pull slowly. So we actually have a name for these two things in physics. The quick pull, because it emphasizes the inertia of the mass, is how we're going to call that the inertial mass of the ball. The slow pull, because it emphasizes the role of the weight of that ball in the experiment, we're going to call that aspect of mass the gravitational mass. Now, it's a sort of a subtle and small distinction, but it turns out that mass anywhere in the universe has inertia. The inertial mass is always there. That mass only makes weight, or the gravitational mass is only relevant when there is a gravity field present. So as far as mass is concerned, it really is the inertia that's more fundamental, and you're going to see in your Newton's second law lab that answering some pretty key questions about what the role of the mass is in the experiment will be sort of supported by your understanding of this distinction between inertial mass and gravitational mass.